Wait, no. I'll just introduce you. Good afternoon to all. Are you able to hear the stream? Are you able to view the stream? So, good afternoon, everyone. I am Padmanabhan from IIT Madras. I'm a master's student. I'm current president of IIT OSA student chapter. So, we'll be so we have started a new series called Photonics Colloquium. So since it is a quarantine time and hope you all are, this is COVID time, and since we are not able to meet, so this is something which we thought of and thought it would be best for all. And we are starting this series inviting eminent researchers from different colleges. First up, I would like to invite Professor Shanti Bhattacharya, who is a professor at Department of Electrical Engineering, IIT Madras. It is a privilege for us to invite Dr. Shanti Bhattacharya, and she will be talking on shrinking optics expandable possibilities. Hope you all enjoy this talk, and this colloquium will be there will be a initial presentation given by Dr. Shanti Bhattacharya, and then we will have a 15 to 20 minutes questionnaire session. And so you can post your questions during the questionnaire session, and we will make sure that we will answer all of the questions, but in the interest of time, if we are not able to answer, we will take the questions. We'll make sure the question reaches to Prof, and you get it and you get the reply back. So over to Prof. Dr. Shanti Bhattacharya. Thank you, ma'am.
Okay. Thank you, Padmanabhan. So I'd like to thank all of you for taking the time this afternoon to join me as I talk about my work. This is kind of a new experience, talking to a bunch of people, and I'm not able to see anybody, but I hope that this way I'm able to reach out to students who maybe would not have had this opportunity before. I know that I'm talking to a set of students who are all working in the area of optics, so I don't really have to convince you of the importance of optics. However, it's a field that is used in such a wide variety of applications, and things are changing so fast that it is really good to be able to give such talks, attend such talks, because one learns of the advances that are happening, and there are many advances. So I hope by the end of this talk, even if you are in the field of optics, you would have learned something new. And if you're not in the field of optics, I hope you'll be jumping up and down saying that's where I need to be working. So if you talk to a layperson, someone who's not in this field or not even a scientist, and you ask them about light, maybe in today's world, especially with the fact that we connect really only online these days, people are going to be very aware of the fact it's fiber optics, the internet, that is one of the reasons we're able to connect across the world, across the country. And that, of course, is an incredibly important use of light. But there are so many applications in which light is being used, so many ways light touches us, so many ways it helps us. And we're going to look a little bit at that in today's lecture. So I don't want Padmanabhan to panic. This black screen is not a technical glitch. Just to show you that if we were talking to people who are not so familiar with the applications of light and you ask them what's going on, they might say, well, I can think of one use of light, it is for illumination. And that's what light was initially used for, whether it's natural lighting or artificial lighting, it is used for illumination. We've come a long way from there, but in a sense, light is still doing that. It is still illuminating, only it is illuminating now in the sense it gives us information, and it can give us a wealth of information in different areas, allowing us to do things that were impossible or would even seem magical a few decades or centuries ago. So this is kind of just a very, very broad spectrum of a few of the applications, and I've listed them here so that you get a flavor of all the areas light
Huh?
work is used in. The
Yeah, what
microscope, of
happened?
course,
Is
is
her
something
voice
many
coming?
people would be familiar with. Unfortunately, today the pulse oximeter is also a term people may be familiar with. This is a device used to measure the oxygen saturation in blood. And today, with COVID 19 or this virus affecting that, almost everyone knows we need to measure this and measure it often. So this is from my point of view, it's an optical device. Of course, there's electronics in it, but the sensing mechanism is uses light.
Akka.
We use optics for imaging. So the image in the right leftmost corner here is that of a retina. You can use light so that you can go down to the smallest, very high resolution and take images of very small, or you can use light as in this example where a vena has been studied so that the different modes of the vena can be understood, or you could use fiber optics to study the health of very large structures like aeroplane wings or railway lines or bridges. Again, maybe a more familiar application would be that of spectroscopy. This by no means covers the multitude of applications that exist, but it just shows you that there are a vast set of applications, and you can imagine that in order to use the light, it has to be manipulated in a certain way to make it relevant for that application. So it's very different from having a light that I switch on and illuminate a room. I need now to change this light in some way that makes it useful, or collect light from a very complicated environment so that I get the information from it. So that's where the basis of today's talk is: how do you manipulate light? So when I talk about beam manipulation or shaping, we look at initially or some of the early techniques, the techniques that many people might be familiar with. And even when I say manipulate, I want to explain what do I mean. When I say manipulate, what parameters of the light do I have to manipulate? What are the parameters of the light? We're going to narrow down this discussion to a very select group of beams of light called complex optics. They are beams that have very special properties, and we're interested in them because of the applications that they can be used in. So I'll spend a little time introducing some complex optics before going to the main body of this talk, which is the optics itself that is used for the manipulation. And we look at various types of optics before coming to the conclusions. So I would normally say, please interrupt me and ask questions. That's unfortunately not going to happen today, but I would really appreciate if you made sure you typed in those questions so that Padmanabhan can ask them to me later at the end. Okay, so if we look at conventional optics, the optics that most people are familiar with, that is of reflection, of reflective or refractive optics. So you can see in the example over here, you have a parabolic mirror, and Padmanabhan, is the mouse clear? If I move the mouse, is it visible?
Yes, ma'am.
Okay.
Yes, ma'am. Yes.
Okay, good. So you should be able to see this parabolic reflector here. This is actually a very typical design of what's used in a car headlamp. So you have a source here, a bulb here, and then the light gets redirected outward to provide the headlamp for the car. Or so this is a way of manipulating the light coming from the source. Or I could use simple refractive lenses, typically glass lenses. They could also be plastic. And as I could use a single lens or a combination of lenses. And I would choose the combination depending on what effect I want to achieve at this image plane. Maybe I want to have a very large angle of light collected and yet focused on a plane. This was how optics was done for hundreds of years. And it's still how a lot of optics is done. It's not that we don't do this anymore. We still do this. It's just that what you can do with this is limited. And if you want to go to more and more sophisticated and complex operations, you need to be able to manipulate light in ways that you cannot always do or cannot do simply with reflective and refractive optics. So say I had a beam of light and I try to depict that here with a cross section. The different colors are just to indicate different areas of the beam. It's not different colors really. I could think that I wanted to change the beam in some way, in, let's say, reorder. So take this part of the beam and put it over here, and this part of the beam and put it over here. And I could possibly achieve this just by a set of mirrors. So the device I'm showing you below is called the digital micromirror device, and in fact is what the device found in projectors. It has 500,000 mirrors. They're square mirrors, 10 micron side, so very small. And these are what either flip on to a particular location or flip off, and all the mirrors that are on create the image that we see that the projector creates. So this is a simple, actually, well, it's not a simple, it's a reflective device that does the reordering I talked about. But I might want to do something more complicated. And now let's say I have a light beam where the intensity is not uniform. So there's a cross section of the beam. Maybe the center of the beam is much brighter and the corners are much darker. And I want to redistribute the light so that I have uniform intensity everywhere. And you can start to see that using simple optics like lenses and mirrors, it might be quite hard to do something like this. It might even be impossible to do something like this. So if that's the case, then I need to go to some other optics. And in fact, there are applications. So if you look at the light that comes out of a laser, it has a Gaussian intensity. So the typical, you can have other beams, but mostly or very commonly you can get out of a laser a Gaussian beam, which means the intensity profile, if you were to take a cross section, it would have this typical Gaussian cross section. And you may want to use it in an application, maybe it's an industrial application, you want to uniformly heat a surface. And to uniformly heat a surface, you want the intensity to be a flat top like this. So this is actual experimental output. We have used a diffractive optical element to convert this Gaussian to a flat top. You could also convert this Gaussian to a ring focus. Say you wanted to cut a circle out of something. You want to do a corneal operation. You don't need to heat the entire region. You just need to heat that ring. And so you're giving energy only in the relevant area. These kinds of operations, some may be possible with the refractive optics, the conventional optics, but not all of them. So it's clear that we want to manipulate light for different applications. What aspect of light am I going to manipulate? So if you think of it, light is an electromagnetic wave. So I have an expression here. That means the wave has an amplitude, it has phase, and it has polarization. We are going to look at manipulating the phase of the light. Why? Because if I manipulate the phase and I do it cleverly, I can control the amplitude as well. I can control the polarization. In other words, control of phase allows me to control or change that light. So I come in with an incident beam. It has some properties. Maybe it's Gaussian. We want to design an element that will change that incoming beam to some desired output beam. And that desired output beam could be close to the element. It could be along the axis or the direction of propagation. It could be in the far field. So really the task now is, the question we are asking is, what's the transmittance of this element? What's this TXY of this element that converts this incident beam, this given incident beam, into a beam with some desired properties or some desired behaviors? That's what we want to do. And when we say manipulation, that's what we're saying. We want to manipulate the phase such that we get a desired behavior. So again, let's go back to just the basics. Let's say you had a glass slab of a certain thickness and refractive index n, and you have a plane wave that's traveling. These are the wave fronts, the surfaces of constant phase that are traveling. And once it reaches the glass slab, of course, the wave, it's going to slow down in the slab. And then when it leaves the slab, it goes back to its normal speed. So what happens over here? Within this glass slab, the beam phase has changed from what it would have been if it had traveled in free space. Why? Because the glass slab has a different refractive index n and it has some certain thickness. So the phase has changed, but this is not mostly going to be useful in any application because the phase changed everywhere across the beam. If I want to use phase change, if I want to cause something to happen to the beam, I must make sure a relative phase change happens. And that doesn't happen in this case. So, of course, that's what a lens does. And again, I have a very simple plano-convex lens here. The wave is incident on this side of the lens, but you can see that now different parts of the beam travel through different thicknesses of this glass lens, and that is going to cause the wavefront to bend, and you can see that it will go, in this case it focuses down to a point. So now the question can be, well, to manipulate phase, we are going to change the path length of this light in some way, and from this example I can see that means deciding what is the radius of curvature of this lens, or in other words, what's the shape of this lens, and what is the material, the refractive index. So now I'm getting a little bit closer to how I affect phase. So we could sort of summarize what I've said up to this point by saying, okay, I need to have a lateral distribution, a lateral variation of phase, and I'm going to achieve that lateral variation of phase using the fact that if I have a material in a certain place, it will have refractive index n, and let's say in the regions around it's air, and these regions where I have refractive index n, so in this case I have a series of cuboids, let's say they have height L and they have some width, they have some spacing. So I have the geometry of the structure, I have the shape of these structures, I have the refractive index of the medium surrounding the structure, I have the refractive index of the material itself. And if I can find some way to create a phase structure like this, I should be able to manipulate light. And of course, the question next will arise, how do I get the correct phase structure? So just to highlight again, when we say manipulate, we want to tailor or control the intensity of the output beam, the phase, the polarization, even the direction that it takes. And the parameters we're going to use are the geometry of a structure, the shape of that structure, and the material or the refractive index. Okay, so I know I can change phase in this way. But how do I get the phase that I want? I say I have a Gaussian beam to start with, and I know I want a beam that does something special. I know exactly what I want it to do, but how do I get this transmittance, TXY? So there are many different ways of arriving at the transmittance. I could start with a known refractive profile. So I can take a plano-convex lens and somehow convert this to a simpler phase or a more basic phase structure, and I'll talk about this in a little more detail later. I could use an analytic expression. So here, for example, is the field expression for the Laguerre Gaussian beam, and you can look at the phase part of this and say, well, this is the phase I want the beam to have, so let me put this phase onto a surface so that when light interacts with that surface, it will acquire this phase. And often when you use such analytic expressions, you get this kind of a phase structure. So this is just an example. You could say, you could say, I'll use an iterative method. So what does that mean? You know the input beam parameters, you know the output beam parameters, that's what you want. And you could use an iterative algorithm that bounces back and forth between what you want to what you have and calculate what is the transmittance that transforms the input to that output. So that's kind of one of the common techniques is called the IFTA, or the inverse Fourier transform algorithm. And the phase you get with the IFTA is a more random phase structure, but it looks random, but it is giving you the desired output. Or you could use a forward technique where you use some kind of intense modeling, a finite element modeling, or a FDTD technique, where you start out with some assumption of the transmittance and look at the output and then keep changing this till you get the desired output. So you can see there are a number of different ways to arrive at the phase that you want. And when I say phase that you want, I mean the phase that will give you the desired complex light output. How do you now realize that phase? That means convert that mathematical expression of phase into an actual device. Well, again, you could, if it was refractive, you could think of just a kind of machining. Or there are a number of lithographic techniques. I've listed the ones out here. They have much higher resolution used when you're dealing with very small feature sizes. These are the techniques that we will discuss or will come up in today's talk. These are static techniques. That means once you design and fabricate an element, the element has that behavior. You can't tune it, you can't change it. But of course, very commonly used are also tunable elements like the spatial light modulators and digital micro devices. This have the advantage that you can tune, you can change, but the spatial light modulators are very expensive. They're bulkier than making elements through lithography. So I will not be concentrating on the tunable elements. In a lab, we might use a spatial light modulator to quickly test out something, but we are interested in making elements that can actually fit into instruments or be used in applications, and therefore we are more interested in the compact static devices. So that's where the focus of today's talk will be. So now with that background, where are we? I'm going to focus on complex light beams. And again, that is light beams with tailored properties, these properties in particular. We are interested in complex light beams because of many very exciting applications. I've listed a few of them here. Say particle trapping, you want to capture a virus and study it. And virus is the word, unfortunately, of the moment. Something like STED, which is very high resolution microscopy. It is resolution beating the diffraction limit of light. And the funny thing is you're doing that with a diffractive element. Or something like light sheet microscopy. And why do we want complex light in these applications, or why do they give you advantages in these applications? It's because of their very unique properties. They are diffraction resistant. The airy beam can actually accelerate as it travels. Airy and Bessel beam self-reconstruct or self-heal. So that means if there's an obstruction in their path, they can actually recover after the obstruction. Or the Laguerre Gaussian beam, which has orbital angular momentum. So who would have thought you can make a little typhoon out of light and then use that to trap a particle and hold it in place and study it, right? So it's these properties that make us very, very interested in complex light, and that's what we're going to focus on. So for the next few minutes, let me very briefly introduce complex light to you. I'm not going to do justice to it. There are, of course, you could give a whole course on each one of these beams, I think. So I'm just going to introduce them to you in a few slides, just so that you get an idea of their unique properties. So the airy beam requires a cubic phase. And this is a picture of a mask that we use to create an airy beam in our lab. So there's actually a cubic phase variation over here. So if you were to make an element with this cubic phase variation and have light incident on it, so this is the element, light is incident on it. This is how the light would travel after the element. So it's actually changing direction. That's what we mean by accelerating here. But more than the change in direction, this central lobe tends to not diffract. That means as it travels, tends over a particular distance to retain its narrow shape, unlike a Gaussian beam, which will tend to diverge or spread out as it travels. Now, the airy beam gets used a lot in imaging, and you can think of sending this into a highly scattering medium like a tissue. And since it's not diverging or not diverging as rapidly as a Gaussian beam, it can travel much further through the scattering medium, and we are able to get information back before the beam is scattered and become too weak to provide us information. If you look at a cross section of a two-dimensional airy beam, it's going to look like this. So this shows you the self-healing property. This is the two-dimensional airy beam. This is the central lobe, the highest intensity lobe. And in the image below, you can see this lobe has been blocked. And this is just 20 millimeters after the block. You can't see that lobe because of the block. But as the beam propagates, you can see that that region starts to reconstruct. And again, if you think of sending this light through a tissue, and if this got scattered by something in the tissue, you wouldn't be able to get information from very deep within the tissue. But because of the self-healing property, you're now able to go in deeper. Because of the diffraction property, it also has better resolution. And in this work, presented already 6 years ago, you can see they compared a light sheet microscope with a Gaussian beam and an airy beam, and you can see the clear difference of the advantage of using the airy beam because of the much better resolution here. Okay, the next beam that I want to talk about is the Laguerre Gaussian beam. This is the beam that has orbital angular momentum, and really that lies in this factor over here, this exponential IL theta. The phase that generates this beam is a spirally varying phase. So in this picture, the phase varies from 0 to 2 pi, but it could even be multiples of 2 pi. It doesn't have to stop at 2 pi. This is the beam I call a little typhoon. It actually rotates, spirals around, the energy spirals around as the beam propagates. It's quite hard to fabricate this structure. So often people interfere, and in this picture over here, this is the phase has gone from 0 to 2 pi and then back to another 2 pi. So it's actually twice 0 to 4 pi. It's hard to fabricate this. So they often interfere this with a plane wave, which is shown here. And the resulting pattern is this fork-shaped grating. You can see an experimental result on the right side, and the output of this in the orders will be this beam with orbital angular momentum. You'll understand a little later why there are so many orders, but this you can also confirm that it actually has that property of orbital angular momentum. From this image, you just see the ring of light, but of course you can also see that it has you can do further experiments and find out that it actually has that 2 pi phase variation, and it actually rotates as it travels. Okay, the Bessel beam is another beam commonly used now, and maybe the best way to describe the Bessel beam is to compare it to the Gaussian. So I have the Gaussian, maybe many of you are familiar with this. So the Gaussian beam, this is the waist in this figure, and over a distance of the Rayleigh range, the divergence is less, but after that it rapidly diverges. The Bessel beam, if you started out with a Bessel beam of the same width as the waist, it would not diverge over a much larger region. And this image on the right, or these graphs on the right, I hope can show you that. So the cross section of the Bessel beam, it also has a high peak central lobe, and then it has rings of much lower intensity. So if we take the cross section across the center of this, that's what is plotted in the graph below. The Bessel beam is in purple color, and I've started out with a Gaussian beam of similar width at the waist, and at the waist, both of them lie one over the other. And at this point, the Gaussian beam is looking better because it has no side lobes. But as the beam propagates, you can see that the Gaussian beam is spreading out quite rapidly. And although the peak of the Bessel beam is dropping, that central lobe is still quite narrow. And again, this is very, very useful if you want to image into a scattering medium. or send light over a larger distance than you could a Gaussian beam without diffraction. So very briefly, I've introduced to you three types of complex light: the airy beam, the Laguerre Gaussian, the Bessel, shown you some of their properties. And now you can come to the question of, well, why do we need to change the kind of optics we use? So I've already said some of the optics, the refractive optics, some of these beams cannot be generated by refractive optics. But even in some cases you can, but you still might prefer to use diffractive or meta-optical elements. And there are a number of reasons for this. The first reason, of course, is clear. If I can't do it with refractive optics, I have to look for an alternative. But diffractive and meta-optical elements are much thinner, much more lightweight, much more compact. So if I'm putting it into a system, especially if I'm putting it into a handheld system, I might want to switch to this kind of optics. I can create many functions simultaneously in diffractive and meta-optical elements. So I'm replacing several elements with one element. And as I'd mentioned earlier, you can even use diffraction to beat the diffraction limit in image. So these are some of the reasons why you would say, let's not do the conventional refractive elements, let's switch to something else. And I'll give you just a flavor of that. I already introduced the Bessel beam to you. In the Bessel beam, while that central lobe, so as the beam is propagating along this axis, the central lobe of the Bessel beam stays quite narrow within its depth of focus. But what is also happening is that the peak of that central lobe keeps decreasing. And this figure over here shows you that as the beam propagates, the peak of that lobe is falling, and you can see it falls quite rapidly. So the lobe is narrow, but the peak is quite, the peak intensity is less. So the Bessel beam is generated by an axicon. That's the element in blue here. It's also known as a conical lens. And you could have a refractive version. It's hard to do in refractive because this angle is very small, but it is possible. But I cannot control with this element the intensity of that central lobe. And this fall off is not going to be useful if I'm trying to image through the depth of something and the intensity of the beam is falling as it travels. It's going to fall anyway if there's scattering, but this is a fall without any scattering. So what we did was use a diffractive element to change the intensity of the beam falling on the axicon, such that we could actually throw more light later down into the path. And here you can and I don't actually know what color this is. So this other color curve, the not blue curve, shows you the intensity of the central lobe of the modified Bessel, where we are changing the intensity falling on our axicon such that the intensity that reaches this region is much less than the intensity that reaches this region. So I can actually throw more light further into the sample. And that was very good if you're trying to imagine a scattering medium where scattering is going to reduce the intensity, but by the very nature of this design, more intensity is being put into the part of the beam further away. So this is some of the things that we can do with diffractive optics. So now let's get into the actual elements themselves, which are the diffractive and meta-optics. So if I look at diffractive optics, what is it? So you can start off with a refractive lens and say, well, if I look at this region here, or this region, or this region, what the light sees is a 2 pi phase change. So I could remove these regions and I only keep the regions extra, and that should give me the same behavior. But it's very hard to fabricate these small, smooth structures with abrupt changes. So what we tend to do is to binarize this and say any height above something, we will treat it as a phase change of pi, and anything below that 0. And now my lens, instead of this bulky plano-convex lens looks like this. It carries out the same property. However, of course, because of the changes made, there are also other things that are happening. And one of the most important things to note is I don't just get one order of light, I get several orders, and the desired behavior is only in one order. What does that mean? The efficiency is poor. So it's easy to fabricate this two-level structure. Any lithography will do. But the efficiency is poor because what I want is going to happen only in one beam and not, uh, and there are a lot of wasted beams. I could think of doing multi-level, but there are issues with this, and I'll come back to that later. So the bezel beam is generated with an axicon. I could do the same operation here. Again, it's hard to fabricate this, so I do a binary version. And this is an example of something from our lab. You now should be able to see where the small or shrinking optics comes. It's not in this case in the outer dimension of the optics, but in the feature sizes. This was an element to work with 633 nanometer wavelength of light. And you can see the feature sizes, these structures are in the tens of microns. So to go back to this picture, we are now, I hope, have a better clue of why we need to shape it, how we can shape it. But I want to address this issue of material. There are only limited number of materials that we can use. A, because they are good optical materials, don't absorb, work in the region, the wavelength regions of interest, easy to machine. But I can trick or I can engineer the material by going to structures which are smaller than the wavelength. So the structures I talked about so far, they were all much larger than the wavelength. But if we now start making structures much smaller than the wavelength, and this is just schematically, we've drawn a blue curve here to show what the wavelength would be. And you can see the structures of this particular grating. This is a grating fabricated in our lab. They're much smaller than the wavelength. So what light sees now is not the if bulk refractive index of the material of each of these structures, but rather an effective index. And in fact, each polarization sees a different effective index. And this means I can make structures or elements that will separate polarization or convert circular to linear polarization and so on. So in a sense, I'm engineering the material. Okay, so up to this point, we've looked at diffractive optics, and I've kind of thrown in now that idea of small optics because of the feature sizes. But I could also think of, well, how do I put optics onto very small surfaces, for example, on a fiber tip? Why would I want to do that? Well, a fiber is made of glass. It can survive very corrosive, harsh environments. It can be used in endoscopy, so it can reach inaccessible places. And if I want the light coming out of this fiber to have special properties, I don't want to have the fiber and then separate free space optics. I want to be able to put the optics directly on the fiber. And we have done this. Some of this work was done here at IIT Madras, some with collaborators in Germany. And you can see an axicon, so those ring structure has been fabricated directly on fiber tip. Again, small optics, shrinking optics, but now we're not talking only about the feature sizes getting smaller, we're also talking about the dimensions getting small. So there's a core of a single mode fiber and 10 micron diameter. Okay, so how do I write these? In the case of the image before, it was written with focused ion beam. So focused ion beam or lithography plus etching allows me to write directly into a substrate, but I could also write with lithography into a resist. And this is some work done by others with focused ion beam. This is some work that we did. And I wanted to show you this because this is now a spiral phase. So it's a 0 to 2 pi variation in a fiber on the core using focused ion beam. But the interesting thing is this is actually a refractive element. It's not diffractive, it's a smooth variation. And we've used focused ion beam, which is a machining technique to actually machine away smoothly and create this refractive element. The spirally varying phase creates a Laguerre Gaussian beam. So this is the output of the fiber. And we did an interference experiment. You can see the phase is actually varying from 0 to 2 pi. This is work done in collaboration with Central University Hyderabad and collaborators in Germany. Okay, so all of this is very good and fine. We've shown that if I have a 2D variation of phase, there is a lot we can do. But can I have a 3D variation of phase? And this picture here is again on a fiber. Remember, this is 125 diameter, 125 micron diameter fiber. So here's a truly 3D structure sitting on top of the fiber. How are you able to do this? We use a process called direct laser writing. So this image, which I've taken from this website, shows a liquid which has fluorophores in it. And in conventional lithography, for example, if you was to send light through this, so you could imagine in conventional lithography, this would be the resist, but they're using a liquid here to demonstrate why direct laser writing is able to do 3D. So in this first picture, the light is shining through this liquid. And you can see, although there's a region where the focus spot is tight, the light is affecting the entire region, the entire column it travels through. Whereas in this case, it's a non-linear effect, and only in the volume of focus where 2 photon absorption happens, and that will only happen when there's high enough intensity, and high enough intensity is only happening at this focal point. So you can see that the effect is only at this point. So if you have a scanning system that allows you to move this point in 3D, you can actually expose in 3D and create these really beautiful 3D structures. So we thought, how can we use this? So let's pull together all the ideas that we've been discussing so far. I can play around with material or refractive index by using sub-wavelength structures. I can affect polarization. However, if I have a polarization element and I have light in order for it to separate, it's also important for the incident beam to come in at a fairly large angle. So if I wanted to separate out light, the polarization of the light coming out of the fiber, I couldn't have this angle of incidence. I need, in this particular design, to separate T and TM light, I need a 56-degree angle. But in the fiber, the light is going to be incident normally. So I couldn't achieve 56 degrees. But because I have this ability to do 3D writing, what if I put one element directly on the fiber tip? It will send the light at the correct angle to a second element that is held at a height above. What's that second element? It's the sub-wavelength grating that does the polarization splitting. So we came up with a model for the polarization grating that is using the simplified modal method. And you can see the numbers are quite stringent over here. The width of these grating lines are 370 nanometers. It's quite a high aspect ratio because the height is 1.76 microns and the period is 0.9 microns. So you have a very tough fabrication here, but it is possible. If light is incident on this grating at 56 degrees, the two polarizations will separate out after the grating. So how do we tilt the light immediately leaving the fiber? Well, we could use a refractive prism, but we decided to go with a diffractive version. So not binary, a diffractive version. And this was the blazed grating that we wrote on the tip of the fiber. But you can see that we wanted light to go into one particular angle, 56 degrees. These are the two different polarizations. They are indeed going at that angle, but you have a lot of unwanted light in this 0th order. So this didn't work for us. So instead we said, let's not use this idea of refraction, because it may not be that efficient, but let's use this idea of refraction where we put a prism and totally internally reflect the light and send it in the right direction. So this is what our idea was. This is a schematic. This dark gray circle or part of a circle you see is the top of the fiber. We want a prism so that light hits the edge, totally internally reflects, and then makes it to this subwavelength grating. And this shows what happens to the different polarizations. The TE will be deflected into the first order, the TM continues in the zeroth order, and you've achieved polarization separation. So we actually fabricated this. So I'm showing you the steps one by one. This was just the prism. This is a colored SEM image. This shows you the subwavelength grating on the top, and this C-shape mirror image C shape is just the supporting structure that holds the subwavelength grating at the required height. We then sent in polarizations TE and TM, and you can see that there's a very good separation here. There's nothing in at other angles. There's a little bit of crosstalk, but in general, the efficiency is very good. Okay, so a quick recap. We started a bit late, so Padmanabhan, would you like me to wind up in 5 minutes? In which case, maybe I skip the next section, or should I go on for another 10 minutes?
I think it should be fine, ma'am. Since we started 5 minutes late, I think you can take 5 more.
Okay, I think we actually started some 10 minutes, 15 minutes. Yeah.
Okay.
Yeah,
you can continue.
Okay.
Thank you. Yeah.
Okay. So let me ask this. What's wrong with binary diffractive optics? I mean, it's doing things that refractive optics can't do. So why look for anything else? You've already seen in some of the examples I've shown that you have light going into the zeroth order. You have higher orders. You will always have these higher orders. I can design my elements so that the zeroth order is taken care of, but I'm going to always have these higher orders. And that means it's always poor efficiency. If you think about it, that grating is nothing like a square pulse. So if I take a Fourier transform of it, that square pulse is made up of all these sinusoids, and those are all the orders of the grating. So I cannot get away from that if I use binary structures, right? The answer might be then, if I can fabricate binary, let me do the binary repeatedly and get multi-level. This structure is much closer to this blaze grating up here, and it will give me much better efficiency. But of course, creating these many levels is very hard to do fabrication wise. I need much higher resolution. It's much more time consuming, and therefore it's not always an option. And that's where meta optics comes into play. So this is work done by a PhD student of mine who worked both here at IIT Madras as well as in Swinburne University. Okay, so what's the idea here? Huygens theorem is a theorem I think most of you will be familiar with. The theorem states that every point of an advancing wavefront acts as a new point source. What happens if we can engineer those point sources? Then I could manipulate the light again. And that's the whole game we're trying to play, right? How do we manipulate the light? So we're going to use dielectric structures. We're not doing plasmonics. Plasmonics, which have metal structures, are lossy, especially in the visible. So we're using dielectric structures. When the dimensions are close to wavelength, it turns out you have electrical and magnetic resonances, and that can create a scattered beam, but you can now scatter it in a way that is different from the incident beam, and therefore you have manipulated or changed the light. So if you look at this, I'm going to play a little video here. This is a particular atom. In this case, it's called an atom. It's a nano atom or a meta atom. This meta atom is a cross shape in this example. It could have different shapes. If you have a certain size, it turns out you have the electric resonance and a magnetic resonance, and they each give a maximum of a phase change of pi. But we know that to get a full phase function or distribution, I must be able to achieve 0 to 2 pi. So if I tailor the size and see what happens, as you're tailoring the size, the electric and magnetic resonances are changing position, and for one particular size, they overlap, and you get the full 0 to 2 pi phase change. And so you need to model and simulate and find out what is that size. Your atom could look like this, it could look like a little cylinder, but you basically need to find out the geometry such that you get the place where the magnetic and electric resonances overlap, and that means you can get 0 to 2 pi. The other clue here, getting that full distribution of phase, because if I want a phase structure, I need to have places where the phase has phi 1 and another lateral position it should have phi 2, another lateral position should be phi 3, and so on. That means I must have this full distribution. How do I achieve the distribution here? I achieve it only by changing the lateral size of the meta atom. That's the whole game here in meta optics. So if I wanted to create a prism like this, in diffractive optics, I would change these heights. And that was hard to do fabrication wise. But in meta optics, I just need to change the lateral dimension and I can achieve it. It's a binary structure. It's a one mask process in a lithographic machine. But I can get different lateral sizes and therefore different phase. So in this example of a spiral faceplate, I've divided it into sectors, and each sector would have cylinders of one size, all binary nature. Or in a prism, you can see that this changing size of the cylinders here means a phase is changing. So let me, maybe in interest of time, not go into the details, but you need to create a phase table where you look up, you can have the different sizes of the, in this case, cylinders, the phase each size corresponds to, the transmission of these sizes. Ideally, you want this to be a straight line transmission 1. It's not possible to achieve, so you have to model and get to the best, the straightest line you can. Once you have this, you can create any phase structure using this as a lookup table. We've done that to create Laguerre Gaussian beams using the fork grating, and each column represents a different number of levels. So the middle row shows a zoomed in version of the central fork. And you can see the 8th level, the beam, so the same power was sent into each of these devices. You can hardly see the output of the 2-level beam. It's a very faint ring over there. But for the third case, the 8th level, you see a very strong, a very powerful. You can get efficiencies well over 96% with just 8 level. And that just shows you some of the sizes of the cylinders used. So let me summarize now. I've taken you, I know, through a lot of information. We've looked at complex light, how to design complex light. And at IIT Madras, we have worked on how do I study the propagation of light? How do we develop the algorithms that generate the phase? We have software freely downloadable, I might add, to help you with your meta optics fabrication design, your diffractive optics design. We've looked at how you can use diffractive optics instead of refractive optics. One reason to do that could be that they're compact. You could do sub-wavelength diffractive optics that allows you to tune the refractive index and in effect play around with the materials. You can combine different operations. I didn't talk about this particular application in this talk, but here there's an axicon and a lens combined in one element and gives you a very focused ring. You could put diffractive optics onto a fiber tip. This is with direct laser writing, so you're doing 3D printing, or you could use this kind of a structure. In either case, you've got small optics from every aspect. The feature sizes are small, the outer dimensions are small. You could do complex light generation using meta optics, so you're doing binary structures, but you can get multiple phase levels and therefore have highly efficient structures. And so to really summarize, you could do complex light, you can do whatever you can imagine light. What is important is to figure out what is the phase that is required to generate that light. And once you have that phase, what fabrication method should I use? And of course, all of this is linked to what is the application. Please do check out our website. There's a lot more information about some of these topics there. This is my group, some of my past students and my current students. A lot of the results I showed you today was the work of Vijay, Gayatri, and Raghu. They were all PhD students, and it's their results that I have shown you today whenever the work was done at IIT Madras. I have to acknowledge my students, my project staff, my funding agencies, and of course, all the different fabrication centers that I have used within the country and at my collaborators' places in Germany, as well as in Australia. So to conclude, this talk covered so many different topics. I may have addressed some of these and used the terms actually use those terms, or they may have been buried or hidden behind them. We discussed refraction, diffraction, signal processing, meta-optics, the dielectric meta-optics works on the principle of Lie scattering, so there was scattering theory there. None of this would be possible without the very sophisticated lithography tools. So many different ideas and topics and fields have been involved. And that, of course, means there's lots of research opportunity. So we are always looking for MS and PhD students. Please, these are some of the projects I have running now. There are more, of course. Please do contact me. Please do apply the next time we have MS PhD rounds of where we take in students, which will happen later this year. And with that, I thank you very much for your patience.
Thank you, ma'am. It was indeed a wonderful presentation from you. So we have some multiple questions posted. Can you hear me?
Yes, yes.
So the first question we have is, excuse me.
Maybe I can go off full screen.
Yes, ma'am. Yes.
And if they have a slide number, I can also go to that slide
there
number.
is no. I think there is no specific slide number based questions.
Okay, fine.
So yes,
let me switch on my camera so that people can at least see who was boring them for the last 1 hour.
Sure, ma'am. not boring indeed. So the first question is, another issue with diffractive optics is wavelength dependence due to 2 pi criteria. Can we quantify the beam quality degradation with respect to wavelength component to refractive optics?
Okay, so that's a very good point. I wanted to mention it. So one of the big differences with diffractive and meta optics is when you go down to looking at phase in this way, it becomes very wavelength sensitive. There is work in both these fields. So you have something called harmonic diffractive elements, which will work at several multiples of wavelengths, and so won't work only at one wavelength. But the chromatic aberration, the aberration caused by change in wavelength, is very bad for diffractive optics. So I can't give any numbers to quantify it, but the kind of chromatic aberration you'd see in a diffractive element compared to a refractive would be much, much higher. So unless you design specifically to take that into account using some kind of harmonic diffractive element, you mostly would use these in applications where you have a single wavelength. There is more work in meta optics so that they make broadband, because these are now resonance structures and they can use a combination or have different layers where you have one layer with one set of cylinders for one wavelength and another layer with a different set of cylinders for a different wavelength. So there's a little more work for broadband structures with meta optics. But yes, you have to carefully consider that in your design if you want to work with many wavelengths. or more than one wavelength.
Thank you for answering the question, ma'am. So I would like to post you another question. To fabricate new structures on the tip of the fibers, should the writing be done along with the fiber fabrication, or can it be done independent to the fiber fabrication?
It's done independent of the fiber fabrication. So all of the results I showed you, we had taken the fiber and either coated it with something, or depending on the process that we were using, but we take the fiber. The fiber fabrication is a standard process and you don't want to mess with that. We buy the single mode fibers and then you use some lithography system to write on them. So that's two independent processes.
Yes, ma'am. Thank you for answering that. The next question is, for meta surfaces, the far field pattern may be considered as interference of multiple wavelets. How important is the spatial coherence of the incoming light? Is there a minimum requirement?
So this is actually true for both diffractive optics and meta optics. You can consider that it is overlapping of different beams that create the desired pattern. Coherence is very important. Again, because you mostly design these for monochromatic sources, you are designing them for sources which have higher coherence in general.
Thank you, ma'am. And we have another. We have a general question. In which field or area of application do you think meta optics will become prominent first?
So it is currently used. So when meta optics started, it didn't start with the dielectric structures. It started with the plasmonic structures. And I know a lot of the applications in that case were in sensing. So because it behaves in a certain way because of the refractive index, and a change in that will cause a change in behavior. So if the medium or something in the environment changes, the refractive index changes, and therefore you can use it as a sensor. So a lot of the initial work was in sensing when it was with plasmonics. But as I talked in today's presentation, meta-optics is now being used for generation of complex light. So I'm not sure where meta-optics which application will take meta-optics and really exploit it to the fullest. I think anywhere, I don't think it's meta-optics. It's meta-optics, diffractive optics, refractive optics. Any of these, they play a role in creating something that we want. In this case, manipulating light in a certain way. It could be any of the applications. It's used a lot, say, in imaging. And I wanted to point out, and maybe I can use this opportunity to stress, the applications I talked about, the work that we've done, though I said shrinking optics, and I spent a lot of time on diffractive and meta optics, quite a few of my solutions also had refractive optics there. Right? We had the small prism on the fiber. It was refractive optics. So it doesn't matter which one you use. It's not that I don't think one solution is better suited to a particular application necessarily. In this case, if it's like creating complex light, anywhere you need complex light, you need something compact. It's to work with a very select range of wavelengths. Meta optics would fall or be perfect for such applications.
Thank you for answering that, ma'am. I don't see any other questions here. Maybe we'll wait for a few seconds for if anyone is interested, they can post their question, or else we would like to wrap it up. Yeah.
Okay.
We'll wait for a few seconds.
Sure.
Yes, I don't see any other questions coming up. So we would like to wrap up by saying thanks a lot for kickstarting our Photonics Colloquium during this tough times. And I hope all of you enjoyed this talk, and we request you to subscribe our channel for further colloquiums, and we'll be having it as a monthly event. And so that's all. We are wrapping it up. Thanks a lot, ma'am. Thanks again. And
Thank you for organizing it.
thank you, and hope all of you are stay safe. Okay, wait. Stay safe and take care. Okay, ma'am. Thank you, ma'am. Thank you.
Okay, thank you.